Alright, so we learned schur function, the classical definition as the quotient of two determinants, and then we showed the Jacobi through the identity, and then using non-intersecting Lorentz path, we showed that schur function is indeed the generating function for all semi-standard Young tableau. Okay, this can be actually taken as a definition. So if you don't want to talk about this determinant and things like that, so if you're only interested in combinatorics, then you can consider this as a definition, and then you can still prove many things. All right, today and then in the second lecture, we will prove the MacMahon's box theorem. We give another proof of this using schur functions. All right, okay. So one can, like I said, one can consider schur function this as a definition. As the definition of schur function. And of course, in this case, we can obviously consider the infinite number of variables as lambda. This is just all semi-standard Young tableau. Entry can be any size. Can be like that without restriction to this. And it is possible to prove. So suppose that we have defined schur function in this way. But in this way, it is not clear this is a symmetric function, because x1, x2, if you change x1, x2, that's not going to be a semi-standard Young tableau. Right? So it's not clear whether this is a symmetric function. But you can prove this using just combinatorics, that it is indeed a symmetric function. That is one of the homework problems. And the principal specialization of S lambda is this. S lambda, we plug in 1 q squared dot dot dot, or yeah, up to q to the n minus 1 if you have just n variables. So we will consider this as lambda 1 q dot 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 q to the n minus 1. That's the principal specialization of this thing. So we have only one variable here, q. And let me define some semi-standard. We already know semi-standard Young tableau is a filling with this strictly weakly increasing, strictly increasing along column, right? And reverse semi-standard Young tableau. This means you just reverse the arrow, so it's like this. Okay, and then we will also define plane partition. We already know plane partition. What is the inequality? The direction of the inequality. Weakly decreasing for plane partitions, right? Because the number of boxes stacked here will be the largest. So it's weakly increasing along each row. Oh no, decreasing along each row and column. And we also define strict plane partition. Weakly increasing, decreasing along rows, but columns is strict. And similarly, we can define reverse PP. We just reverse the arrows, the direction of the inequalities, and reverse, a strict reverse. Strict reverse RPP. Let me just say RPP. reverse plane partition RPP. So reverse. But you can notice here that some of them are really the same. Like semi-standard Young tableau is exactly the same as strict reverse plane partition. So we don't have to say, you don't have to use this because it's already there. Semi-standard Young tableau is more common. So we are not going to use this. So simply says. And also, what is this? Reverse semi-standard Young tableau is the same as strict, right? These two are the same. These two are the same. So we have only 1, 2, 3, 4 things, basically. All right. So we want to consider plane partition because we want to show MacMahon's box theorem using schur function. But we will work with reverse plane partition first because it is more closely related to semi-standard Young tableau. If you look at the inequality, they are in the same direction. All right. So we will be focused on RPP, reverse plane partition. But at the end, we will consider plane partition for box inside the box. Is this clear? All right. You just need to, because we already know this, we just need to consider this. Oh, and this, and reverse semi-standard Young tableau. We will consider these things. All right. So proposition. L is the number of parts less than or equal to n. Then the schur function, principal specialized. It's kind of similar, but yeah, let's do this. But instead of starting from 1, we start from Q, but they have very simple relation, but I'm going to talk about that later. This is equal to semi-standard Young tableau, a maximum element at most n, Q to this. This means the sum of entries, like plane partition. Okay? I claim that this is the same as reverse semi-standard Young tableau, lambda n, Q, T. Do you see why? These two are, actually, this is really the same as this. Why? Why are they the same? Symmetric function. So maybe we can talk about this first. X1, okay, this one. We already know that this is a schur function is the generating function for this. For x1, instead of x1 we multiply q. Instead of x2 we multiply q squared, etc. That's exactly the power, q to the power of the sum of the entries, right? Example, 1, 2, 2, 3, 3, for instance. This corresponds to x to t. This is x1, x2 squared, x3 squared. But in this principal specialization, we have q squared squared, q cubed squared. This is exactly q to the sum of these, 1 plus 2 plus 2 plus 3 plus 3, which is, we denote just this. So we know this is true. And by the same idea, this is equal to this, right? So they are the same. So for reverse semi-standard or standard, just semi-standard, they give the same thing. All right? And one more thing. This is also equal to, if you want reverse plane partition instead, pi in reverse plane partition of lambda, we use the same notation, n minus l plus 1, at most this. Each part is at most this. But we need to have this factor of q. Why? The only difference between semi-standard and reverse plane partition is the following. So for instance, maybe we can consider, okay, let's prove this. We only need to prove this thing, reverse plane partition thing. Semi-standard Young tableau. There is a very simple bijection between this and this, reverse plane partition. Can you imagine? For instance, let's say 1, 1, 1, 2, 2, 2, 3, 3, 4, 3, 4, 4. You just subtract like 0, 0, 0, 0, 0, 1, 1, 1, 1, 2, 2, 2. You just subtract this, then what you get is you subtract 1, so it's 1, 2, 2, 3, 1, 2, 2. This is a reverse plane partition. We have weakly inequalities. This is in fact a bijection. Okay, the maximum entry is n, but we subtracted this by. Oh wait a second. Is this true? Is this true? Do you think it's true? Okay. Something is. Yeah, I'm a little concerned about this. The maximum element. If the maximum element is here, is okay. But what if we have maximum element n over here? It will be n. So this is not correct, I think. Okay. Reverse plane partition. How can you fix this? Any idea to fix this? Yeah, I think I made the same mistake when I was preparing this, but I also got the same. Okay. For reverse, okay, I'm not sure if I can fix this right away, but let's try. For reverse plane partition, this is okay because the largest element will be always in the first row. Reverse semi-standard, I mean. Reverse semi-standard Young tableau, lambda n, q to the size. This is equal to, for reverse semi-standard, so plane partition, you use pi. Plane partition lambda n minus l plus 1. This is okay. Times q to the I got a little confused. Okay, so let's not talk about plane partitions. Do you have any idea? 뭐. 응. 응. 네. 네. 그쵸. 이거 문제가 지금 뭔지 아시겠죠? 이게 좀 아닌 것 같아서. 그러니까 so eventually we want to have weak inequalities like this at the end. Then we have to subtract this. But what is the maximum element here? We don't know. So, because it depends on each row. Each row we have, the first row we may have n at most. The second row we may have at most n minus 1, etc. This is not a very good situation for us. So we don't want to have that, depending on each row. We want to have the maximum bound for each, the same. But if we talk about, if we consider reverse plane partition, a reverse semi-standard, for instance, so let's say 7, 7, 7, 6, 4, 6, 5, 5, like 5, 4, 4. We subtract, what do we need to subtract? 0, 0, 0, 1, 1, 1, 2, 2, 2, 2, 2, right? Then we get 5, 5, 5, 4, 2, 5, 4, 4, 5, 4, 4. So this is what? This is here. This is what? Plane partition. At most, because we subtract L minus 1 in the first row, and always the largest one will be here. So we have this. And what do we have to multiply? Because everything we have extra power here. This is exactly summation L minus I lambda I think. So yeah, we have this. So I think this is correct. But okay. So let's consider this. But anyway, we will find a formula for this, to obtain a formula for this at the end. Okay, but yeah, sorry about this mistake. Yeah, I think I need to. But by the way, proposition. This is a general fact in schur function. S lambda. If you multiply everything, if you multiply something to every variable like this, xn, you can factor this z outside. Only you need to multiply the size of lambda. This is quite easy to see if you consider the combinatorial property, combinatorial description of this. Because everything must have z, that means z will appear this many times. So this is quite easy. So, yeah. So S lambda 1 q dot 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 q n minus 1, there is a very simple relation between this and this. This is just equal to this. So this and this, they are really the same up to just a factor. So we will look at this. Okay? We will compute this. We will find a formula for this as a product using the original definition of the schur function as the quotient of two determinants. All right? Now let's go. Theorem. S lambda 1 q dot 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 q n minus 1 equals q to the I minus 1 lambda I from 1 to L pi 1 minus q I j plus j minus I 1 minus q j minus I. So I less than j from 1 to n. We have a nice product like this. We're going to prove this using this formula. We know that it is the quotient of these two alternate. What is this? Determinant. So we need to evaluate two determinants. One is, we already know. N minus j. This is the Vandermonde determinant. We already know. We only need to compute this. So let me recall you the Vandermonde determinants here. Determinant x, this thing, I n minus j. This is equal to xi xj, where I less than j. Okay. And also, if you reorder the columns backwards, then we get this xij minus 1. This is the same thing with columns in the reverse order, right? So this is the same, exactly the same, except you just change the order, xj minus xi. Only the sign changes, but that's exactly reversing this thing. We're going to use this. Okay, so we are interested in this, so let's see what happens. Determinant of what? So here we have q to the I, lambda j plus n minus j over determinant q to the I, n minus j, right? This one is easy. We know what this is. But what about this? This is indeed, in fact, a Vandermonde determinant. So let me change this a little bit. Oh wait, yeah, we have minus 1, right? Because it begins from q to the 0. Okay. So we need to compute two determinants here. So the first one, determinant, this thing over here, the numerator. Let me change the order. Let me move this inside, and I'm going to change I'm going to exchange I and j. Doesn't matter because the determinant is still the same. J minus 1, that thing, right? I just changed these two things and I and j. This is exactly of this form over here. If you think of this as xj, xi, right? So this one is equal to determinant I less than j. You write j first. So xj is q to the lambda j plus n minus j. Lambda xi is lambda I plus n minus I. All right? What about this? No, it's exactly this thing. Q to the I, Q to the j. So we computed this. All we need to do is to simplify the product. Right? Is it okay? But here, let's simplify this by factoring this out. You know, this is smaller than this. because j is bigger, this is smaller. So let's factor this outside. Then I less than j, q to the lambda j plus n minus j, 1 minus q to the, we factor this out, so lambda I minus lambda j plus j plus minus I. You see that this vector appears now. And what about this? We factor I out, get the I out, j minus I. Now if you divide this by this, then by doing some computation, you get this. Oh, by the way, I made a mistake. Yeah. Then you will get this. That's it. That's the proof. Question? This is just a computation using Vandermonde determinant. Okay, now I have some trouble with this mistake. Okay, I'm not sure if I can fix this right now. There is some mistake, but this can be fixed. Do you know what I mean? RPP 0. Yeah, let me just do this anyway. There is some kind of mistake, but we should be able to fix this. This is the set of reverse plane partition of shape lambda entries are between n and 0. Here 0 means we may have zeros. So like this. 0, 0, 1, 1, 1, 1, 2, 2, 1, 2, 2, something like that. This shape is fixed. Largest entry is fixed. 0 is there. Corollary is this. We just use the previous theorem, then we get this. All right? So we have a generating function for RPP as a product. Now we can prove MacMahon's box theorem again using this. Another proof of MacMahon's box theorem. All right, now we will consider this. Lambda equals A, B, N equals C. This means lambda is this, A times B. Lambda is this. And C is the height of your plane partition. So so then here, what does that mean? Lambda is in RPP, A to the B, N. This means, so this is a box. This is inside the rectangular shape, right? So if you rotate this, like for instance, lambda equals 0, 0, 1, 2, 1, 2, 2, 2, 3, 3, 4, 4. This is pi. Let's pi star be the object obtained by rotating this 180 degree. If you rotate this, 4, 4, 3, 3, 2, 2, 2, 1, 0, 2, 1, 0, 0. This is now a real reverse, the usual plane partition. So this is plane partition inside the box A, B, C, like this box. A, B, C. The height is C. So we really, and of course their sizes are the same. So this is in fact the generating function for reverse plane partition over here. All right? all remaining is to compute and simplify or modify this product. Okay? So let's do this in the next page. So the theorem, this is MacMahon's box theorem. Plain partition inside this box, A, B, C, Q to the this equals, we know 1A, 1B, 1C, 1 minus Q to the I plus J plus K minus 2. We can express that product in this way, in this form. So in the previous theorem, if lambda equals A, B, we here we just plug in this thing, and this thing over here. All right? Then we get something like this. The proof. Our left hand side is equal to product 1 I less than J less than B plus C 1 minus Q. I just replace this. All right? What is lambda? They all have the same part, right? They are all the same, A. Then this will be 0. Is that right? Then this part is this part the same. They cancel. We have 1. What happened? Another mistake? Can you find the correct way to do that? Are they all the same? Like all A? Not really. You have to think carefully. Lambda i's are all A if I is less than or equal to B. Because here, ij are up to B plus C. So, okay, this, we don't have enough space. Lambda I, I is either A or 0. If I is less than or equal to B, I is greater than or equal to B plus 1. And C, up to C. Because, we are considering that lambda is a partition with B parts equal to A and C parts just 1, just 0. So if they are the same, this will be cancelled. So we will only need to consider ij different for I and j, where lambda I is not equal to lambda j. That means one of them must be 0, one of them must be A. How can that happen? I is from 0 to B, and j is from B plus 1 to B plus C. This is the only time when they are different. So in this case, this one is A and the other is J. So now you can just change, like here you can replace J by J minus B and I by like B plus 1 minus I. We just reverse this, then I is still from 1 to B, J is from 1 to C. Now this changes, 1 minus Q. J minus B minus this. So it's going to be J plus I minus 1, right? And here, the same, A plus J plus I minus 1. But you can see now that this is equal to this. That's just a computation. You can write this as the product, like K from 1 to A, like 1 minus Q to the I plus J plus K minus 1, I plus J plus K minus I 1 minus 2. So this is the end of the proof. Okay? Yeah, but I made some mistake here. I'm going to correct this, and I'm going to upload the corrected version of the lecture note. But basically, the idea is this. So using schur function, you can prove MacMahon's box theorem like this. Any question? So it's a powerful tool in algebraic combinatorics. We can use this to solve some problems in combinatorics. All right. And this theorem also shows a very famous formula called Hooke content formula. And Hooke length formula. So let me define some notation. X, lambda is a partition. X is in lambda. This means X is a cell of the Young diagram of lambda. Like this. This is X. This is a cell X. And we're going to define two things. The Hooke length, of X in lambda is denoted H of X. This definition is this: lambda I, lambda J prime. Lambda prime means the conjugate. But there is a better way of defining this. This is the number of cells in this. This is called the Hooke of X. You look at the cells to the left, to the east, and cells to the south. In the same column, same row. You just count number of cells here. That's the Hooke length. And the content of X is just defined to be C of X is J minus I. If it is in ij position, ith column, jth, ith row, jth column. So for instance, X is here. What is the Hooke length? You count number of boxes. 1, 2, 3, 4. So it's going to be 4. What is the content of this? J is 2, I is 1, so 2 minus 1 equals 1. So basically, contents here are all 1, zeros, and these are all 1, these are all 2s, and 3s, etc., like minus 1, minus 2, etc. These are the contents. Okay? So we define Hooke and content. And now, the Hooke length formula. A Hooke content formula. So S lambda 1 comma q comma dot 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 q to the n minus 1. This schur function is I minus 1 I 1 to L is the number of parts. For you take the product over all cells in lambda in the it has a nice product like this. I'm not going to prove this, but there is a problem related to this in the homework set. And finally, the Hooke length formula, very famous Hooke length formula. The number of standard Young tableaux, number of SYTs of shape lambda. So this is the generating function for a semi-standard Young tableau. But here, this is standard Young tableau. This is denoted by f super lambda. This is the product n factorial over all x Hooke length of x. Here, lambda is a partition of n. So for example, this means you can find the number of standard Young tableau very easily So let's say lambda equals this. So let's compute the hook length. Here, hook length is 1, 1, 3, 2, 4, right? This is partition of 5. So the number of semi-standard standard Young tableau is 5 factorial over the product of this hook length, 4, 3, 2, which is 5. There are 5 semi-standard Young tableau. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There are only 5 standard Young tableau, which is computed over here. This is true in general. It's a very well-known and famous formula proved like 1950s, in 1950s. Any question? All right. Let's. Now we are going to consider. So we computed the generating function for all plane partitions inside the box. But there are other classes like symmetric, cyclically symmetric, things like that. We can consider symmetric plane partition. So it's a MacMahon's conjecture. So it is a conjecture like this. This is symmetric plane partition. So we have RRT, Q to the size of pi equals nice product like this. This can also be proved using schur function and determinant. Okay. We need 2 lemmas to prove this. Lemma 1. So first, we need to write this as in terms of schur function, but there is a way to do that. T, RRT. Q, the left-hand side, this is equal to sum over all partitions inside this rectangle. And schur function Q to the 2R minus 1, Q to the 2R minus 3, Q. Like you only consider odd integers like this. Proof. Okay, I need to draw some diagram. You need to have some imagination. So this is symmetric. This is an example of symmetric plane partition, right? It is symmetric. Okay? Symmetric about this line, vertical line. Now, you know, each part, you look at each floor. The first floor is this. First floor is this. And the second floor, or top floor on the second top floor is the same thing, and the third one, the same thing, and the third one is like is like this, right? And the fourth one, 5. 1, 2, 3, 4, 5. I'm going to decompose this into floors like this. All right? Now we know they are all symmetric or self-conjugate. We have a bijection between self-conjugate and partitions with distinct outparts. So here, make this to be just this. Again, the same thing. What is this? Like this. 1, 2, 3, 4, 5, and 3. And here, this, and this. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, and 3. Like that. And one more. Oh no. 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, and 1. Yeah, I think I made a mistake. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, and then yes, 1. Like that. And you just make a plain partition out of this. Okay, that looks like this. Let me try to draw this. 1, 2, 3, 4. And 2 things like this. Like a drawing class. Finally, here. Okay, this is it. So this part is the side over here. So 9, 7, 1, 9, 9, 5, 1, 9, 5, 1. This is 5, 3, 5, 3. This is 3 and 3, 3 and 3. We make a partition, plain partition here. But you can see, all right. So this is, if you rewrite this, 7. Oh no, it's 9. 9, 5, 1, 5, 3, 3, 3. This is a. Oh no, 3 is over here. 9, 9, 5, 3, 5, 3, 3, 3. This is a semi-standard Young tableau. A reversed semi-standard Young tableau. So this is the generating function for this. But this is, what is the maximum size, maximum of this? This was R and R. R, this is T, right? So the maximum of this is this, R. The maximum is 2R minus 1, like this. And what about this? That is, okay, that is this thing. The height is the number of floors. That will be the number of rows here. All right? So this is T, and this is R, at most R, because we have this part. Yeah, there is some kind of, is this right? T, this is right, this is right. I want this to be R to T then. Oh yeah, that's right. Because here it's not really semi-standard. It's a transpose of a semi-standard, right? Because we have inequalities, strict inequalities here, and weak inequalities here. That's why we have T to the R instead of R to the T. We have to look at the transpose of this. Do you see? Yes. Because we have weak inequalities and strict inequalities here. I made this backward. So we have to. That's why we have T to the R, not R to the T. So anyway, this can be written in terms of the sum of Schur functions. Okay. And finally, we need to evaluate this. There is the second lemma. Lemma 2. This proof is quite long. It is described in the textbook, and you need to read the textbook and do the homework for 2 weeks. To R minus J. Determinant. And this is basically Vandermonde determinant type B. We learned this in class if you want, if you remember. This is proof is quite long and it is written in the textbook, so I leave this to you to read the textbook and then summarize the proof. And this can be applied to the proof of the MacMahon's conjecture. So we know that this is equal to this. Oh no, this conjecture. This is equal to this. And we express this as a quotient of determinants. All you need to do is to evaluate this using Vandermonde determinant type B. All right? That's also a homework problem. We need to evaluate the two determinants. Yes. Right. So this kind of approach is very common in this plane partition thing. So most of these 10 classes are proved like this. Interpret this in terms of Schur functions and then change that into determinant and then evaluate determinant. So each step is quite difficult. But anyway, everything has been done. Most of this. Okay? Any question? All right, then next week we don't have any class because it's a midterm week. So we will meet again in 2 weeks. And sorry about the mistakes today. I'm going to fix this and hopefully update the lecture notes over the weekend, hopefully. Thank you for your attention and see you next time.